Hi there. For the last lab of the summer, I have decided to revisit the topic of drag force and incorporate it into a real-life pendulum system. My question is, and my goals are, to predict the change in motion of the pendulum and manipulate the drag force to visually see its impact on the system. My predictions are first, when the drag force increases, that the pendulum will come to a stop quicker due to the increased force against the motion of the object. My second prediction is that decreasing the drag force will allow the pendulum to swing for a longer period of time, since there is not much force acting against the velocity of the object. The fundamental principles that we will be using are Newton's second law, and I will be using it in two forms, which you see here. V final is equal to V initial plus F net divided by mass times delta T, and then the position form, which is R final is equal to R initial plus V average times delta T. And the forces that I will mainly be focusing on are gravitational force and the drag force, and then the net force is those two forces added together. For my video analysis and tracker, I recorded myself dropping a charge block from rest, the charge block parallel from the point of attachment that I'm holding out in front of me. The pendulum's length is about 0.6 meters, and the charge block weighs about 2 kilograms. You can observe the block's motion in the X and Y direction in the graphs on the right and how they change as the block swings. I use the X and Y positions as a function of time from this analysis in my code to compare the real-life model to the computer model that we will look at in a moment. Here's the main piece of code that uses Newton's second law to create the motion of our module. I was advised by another student in TA to use spring force with a high spring constant so that it would be simpler to write my code using previous labs as a reference. I was also instructed to use a damping force to neutralize the rapid motion that was occurring in the Y direction as the pendulum swung. Besides that, we have our drag and gravitational force accounted for, and Newton's second law, which is translated directly into the code, which you can see here are the last two lines. Ball.v is equal to ball.v plus F net divided by ball.m times delta T, which is the same thing as V final, which is to the right of it. And then ball.position is equal to ball.position plus ball.v times delta T, which is the exact same thing of the R final equation that is to the right of it as well. Now let's launch my code and see three different visuals, each with a different drag force. If I am to set the drag force equal to 0, the pendulum would continue to swing because there is an absence of air resistance. Even when I am standing in my house, it might be a little, but air resistance still exists. So this is not a realistic situation. If I increase the drag constant arbitrarily to b is equal to 0.3, there is an increase in opposing force as 0.3 is multiplied by the velocity of the object, thus the object slows down quicker and eventually reaches rest. If I were to increase the drag force even more, say to 0.8, the object would only swing back and forth once or twice and then fully come to rest, as you can see here. Looking back at my predictions, I was correct. When drag forces increase, the pendulum will come to a stop quicker due to the increased force against the motion of the object, and we saw that in the visuals due to Python. We also could see that when I decrease the drag force specifically to 0, the pendulum would swing for a longer period of time, and if the drag force is 0, it would continue to swing without ever coming to rest. Understanding how the velocity of an object is impacted by forces, promoting or inhibiting, it was easier for me to understand the relationship between drag force and how it acts on a pendulum, and that is thanks to Newton's second law.